Alrighty, we're going to be looking at exponential functions in this section. We're going to identify these functions and classify them as either growth or decay. Then we'll learn to evaluate and graph these functions. And lastly, in actually my next video on this concept, we'll apply exponential growth to compound interest. Let's get started by defining what an exponential function is. It is in the form CAX. Now this looks kind of familiar to something else, but we're going to provide characteristics to differentiate. C and A and X are all real numbers. However, C has to be greater than 0, A has to be greater than 0, and A cannot be equal to 1. In just a bit, I'll show you why. So some characteristics. The base in this function is a constant value, and the exponent is where the variable is located. That C value, that's actually going to be our y-intercept, where x is equal to 0. And the A value is going to determine the rate of growth or decay of our function. So let me give you some real examples here. This function f of x equaling 4 to the x power is an exponential function. Notice that the variable x is in the exponent position. Our A value here is 4, and we actually don't really have a C value that's visible because it is the almighty 1. Here you go, this J function, J of x, the C value here is 4. It is removed from the base, which is 1/2, and that is the only item being raised to the x power. This is an example of an exponential function. Here's one more interesting function. It's called the natural exponential function, and it is closely related to logarithmic functions, which we will look at a little bit later on. This is not an exponential function. This is actually a power function because our base is raised to a power, not to an exponent. And here, as I mentioned, I was going to explain why the A value, why your base cannot be equal to 1. Let's recall. 1 raised to any value of x is always going to generate the same value because 1 times itself is always 1. That function is actually a linear function, not an exponential function. So let's look at growth and decay. Growth is on the left, and you'll see that that line is growing, whereas on the right-hand side, our function seems to be decreasing or decaying. That exponential decay model, that should, for those of you that worked on the blood filtration, that should look familiar to you. Let's identify some important points here. The A value for a growth function has to be greater than 1. And our C value is, as you can see, where it has crossed the y-axis. It is our y-intercept. Similarly, for the decay model, our A value is going to be between 0 and 1. It's going to be some kind of rational number, fractional number between 0 and 1. And again, our C value is going to determine our y-intercept for either a growth or a decay model. So the only thing that differentiates between a growth or decay is your A value, your base value. Let's work an example together. This is one of our objectives, being able to find the exponential function. And here we're given some coordinates. Let's take a look at these coordinates real quick. Notice that the x values are -1, 0, 1, 2, and 3. And the y values for those go 1, 2, 4, 8, 16. Notice that it grows in an interesting fashion here. It's not just the same each time by the same amount. It changes. So to determine our function, we first want to find the value of c, and this is going to be the y-intercept, or where your x value is equal to 0. And we're given that point. It is 0, 2. That is the coordinate of our y-intercept, so our c value is equal to 2. Next, we need to figure out our value of a. This is the rate of change. As we progress, our values are getting larger, from 1 to 2, 2 to 4, 4 to 8, 8 to 16. Those are growing. So we're looking at a growth model, and it is increasing. Those outputs are increasing by multiples of 2. That means that our a value is equal to 2. We just plug those in to the function model, and we have f of x is equal to 2 times 2 to the x power. You have to separate the c and the a value, otherwise you will have a very different function. So that was given coordinates. I have one more example for you, and it is when you are given a graph. So again, we take the same approach and we determine the value of c. Well, this is nice. We can see it quite easily on our graph. It is the point 0, 4. That is where our y-intercept is happening, which means our c value is 4. Next, we have to figure out our rate, our a value. You'll notice that this is a decay, that it is decreasing. And if you look at your y-intercept, the next visible point at 2, it went from 4 to 2 as your x increases, and then it goes from 2 to 1 as you increase again your x value. So it goes from 4 to 2, 2 to 1. This is decreasing by halves, so our a value is 1/2. This allows us to provide the function in that model, which is f of x equals 4 for the c value and 1/2 for the x. All right, so that is half of our lesson on exponential functions. Stay tuned for more.